The National Electrical Code, or NEC, requires grounding conductors to be installed between the grounding electrode, such as a ground rod, and all grounded systems and equipment. However, the NEC does not specify a maximum distance for the grounding conductor run, as it depends on the size of the conductor and the type of grounding system used. While the code does not specify a limit, it is generally recommended to keep the grounding conductor run as short as possible, ideally within 20 feet. This is because longer runs increase the resistance and inductance of the conductor, which can reduce the effectiveness of the grounding system. Now looking at a 70-foot run of number 10 stranded wire, this is acceptable for a grounding conductor. Stranded wire has a larger surface area than solid wire, which helps reduce resistance and inductance. However, it is important to ensure that the wire is properly sized and installed according to code requirements. Here are some additional considerations. The direct current resistance of a 70-foot number 10 stranded wire run is less than 0.1 ohms, which is well within acceptable limits. The grounding conductor should be routed in a direct and unobstructed manner to minimize resistance and inductance. Avoid sharp bends or kinks in the wire. Ensure that all connections to the ground rod, grounding block, and surge suppressor are tight and secure. Here are some recommendations. Run the grounding conductor from the grounding block to the service entrance ground rod using the shortest possible route. Use number 10 or thicker stranded copper wire for the grounding conductor. Follow all code requirements for grounding and surge protection. Here is some more information about electrical grounding. Electrical grounding is an essential safety measure in electrical systems. It provides a low impedance path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock and damage. Grounding also helps to reduce electrical noise and interference, which can improve the performance of sensitive electronic equipment. There are two main types of electrical grounding systems: system grounding and equipment grounding. System grounding is the intentional connection of the neutral point of a power system to earth. This helps to stabilize the system voltage and provide a reference point for fault detection. Equipment grounding is the connection of non-current carrying metal parts of electrical equipment to earth. This includes enclosures, raceways, and other metal parts that could become energized in the event of a fault. The purpose of equipment grounding is to provide a low impedance path for fault current to flow back to the source, which will trip the circuit breaker or fuse and de-energize the circuit. Grounding conductors are typically made of copper or aluminum and are sized according to the size of the circuit they are protecting. The grounding conductor must be able to carry the maximum fault current that could occur in this circuit without overheating or melting. The National Electrical Code, or NEC, provides detailed requirements for electrical grounding systems. The NEC specifies the size and type of grounding conductors that must be used, as well as the methods for installing and connecting grounding electrodes. Grounding electrodes are metal rods, pipes, or plates that are buried in the earth and connected to the grounding system. The purpose of the grounding electrode is to provide a low resistance connection to earth. The NEC requires that all electrical systems be grounded, with a few exceptions. The NEC also requires that all metal enclosures and raceways be grounded, as well as any equipment that is likely to become energized in the event of a fault. Grounding is an essential safety measure that should be taken seriously. If you are not familiar with electrical grounding, it is important to consult with a qualified electrician before working on any electrical system. Here are some of the benefits of electrical grounding. It protects people from electrical shock. It protects equipment from damage. It reduces electrical noise and interference. It improves the performance of sensitive electronic equipment. It helps to prevent fires. If you have any questions about electrical grounding, please consult with a qualified electrician. Here is some further information about grounding and bonding. Grounding and bonding are two distinct but related concepts in electrical safety. Grounding refers to connecting electrical equipment and systems to the earth, while bonding involves connecting different metallic parts within an electrical system to create a low impedance path for fault currents. Grounding ensures that in the event of a fault, the electrical current will safely flow to the earth, minimizing the risk of electric shock. Bonding, on the other hand, ensures that all metallic parts are at the same electrical potential, reducing the risk of arcing and fire hazards. The National Electrical Code, or NEC, provides comprehensive guidelines for grounding and bonding electrical systems. These guidelines cover various aspects, including the size and type of grounding and bonding conductors, the methods of installation, and the requirements for grounding electrodes. Grounding electrodes are typically metal rods, pipes, or plates that are buried in the earth to provide a low-resistance connection to the earth. Bonding conductors are used to connect different metallic parts within an electrical system, such as metal enclosures, raceways, and equipment frames. Proper grounding and bonding are essential for ensuring the safety and reliability of electrical systems. It is important to consult with a qualified electrician to ensure that your electrical system is properly grounded and bonded in accordance with the NEC requirements. Here are some key differences between grounding and bonding. Grounding connects electrical equipment and systems to the earth, while bonding connects different metallic parts within an electrical system. Grounding provides a path for fault currents to flow to the earth, while bonding ensures that all metallic parts are at the same electrical potential. Grounding minimizes the risk of electric shock, while bonding reduces the risk of arcing and fire hazards. Both grounding and bonding are essential for electrical safety. Here are some additional details about grounding electrodes. Grounding electrodes are typically made of copper or galvanized steel. The NEC specifies the minimum size and type of grounding electrode that must be used, depending on the size and type of electrical system. Grounding electrodes must be installed in accordance with the NEC requirements. Here are some additional details about bonding conductors. Bonding conductors are typically made of copper or aluminum. The NEC specifies the minimum size and type of bonding conductor that must be used, depending on the size and type of electrical system. Bonding conductors must be installed in accordance with the NEC requirements. Now let us examine surge protection. Surge protection is the process of protecting electrical and electronic devices from voltage surges or transient voltages. Voltage surges are sudden and temporary increases in voltage that can damage or destroy sensitive electronic components. Surges can be caused by a variety of factors, including lightning strikes, power grid switching, and the operation of heavy machinery. Surge protection devices, or SPDs, are designed to divert or suppress these surges, protecting connected equipment from damage. SPD are typically installed at the service entrance of a building, as well as at individual outlets or devices. There are several different types of SPD available, each with its own advantages and disadvantages. Some common types of SPD include metal oxide varistors, or MOVs, silicon avalanche diodes, or SADs, and gas discharge tubes, or GDTs. MOV are the most common type of SPD and are relatively inexpensive. They work by clamping the voltage to a safe level, diverting the excess current to ground. SAD are faster than MOV and can handle higher surge currents. They are typically used in sensitive electronic equipment. GDT are the slowest type of SPD but can handle the highest surge currents. They are typically used at the service entrance of a building. When selecting an SPD, it is important to consider the voltage and current rating of the device, as well as the type of equipment being protected. It is also important to choose an SPD that is listed by a recognized testing laboratory, such as Underwriters Laboratories or UL. Surge protection is an important part of protecting electrical and electronic equipment from damage. By installing SPD, you can significantly reduce the risk of damage from voltage surges. Here are some additional details about SPD. SPD are rated in terms of their surge current capacity, which is the maximum amount of current that the device can safely divert. SPD are also rated in terms of their clamping voltage, which is the voltage at which the device begins to divert current. SPD should be installed in accordance with the manufacturer's instructions and the National Electrical Code, or NEC. SPD should be inspected regularly to ensure that they are functioning properly. Here are some tips for selecting an SPD. Choose an SPD that is rated for the voltage and current of the circuit being protected. Choose an SPD that is listed by a recognized testing laboratory, such as UL. Choose an SPD that is appropriate for the type of equipment being protected. Consider the surge current capacity and clamping voltage of the SPD. Here are some tips for installing an SPD. Install the SPD as close as possible to the equipment being protected. Follow the manufacturer's instructions and the NEC. Use the correct wiring and grounding methods. Inspect the SPD regularly to ensure that it is functioning properly. Now, here is some extra information about lightning protection. Lightning protection is the practice of protecting structures and equipment from the damaging effects of lightning strikes. Lightning strikes can cause fires, explosions, and electrical damage, as well as injuries and fatalities. Lightning protection systems are designed to safely conduct lightning current to ground, preventing it from entering a structure or damaging equipment. A typical lightning protection system consists of air terminals, conductors, and grounding electrodes. Air terminals are metal rods or points that are installed on the roof of a building to intercept lightning strikes. Conductors are wires or cables that connect the air terminals to the grounding electrodes. Grounding electrodes are metal rods, plates, or grids that are buried in the earth to provide a low resistance path for lightning current to flow to ground. When lightning strikes a building with a lightning protection system, the current is safely conducted to ground through the air terminals, conductors, and grounding electrodes. This prevents the current from entering the building and causing damage. Lightning protection systems are typically installed on buildings, towers, and other structures that are at high risk of being struck by lightning. They are also used to protect sensitive electronic equipment such as communication systems and computer networks. The National Fire Protection Association, or NFPA, publishes the standard for lightning protection systems, NFPA 780, which provides detailed requirements for the design, installation, and maintenance of lightning protection systems. Lightning protection is an important safety measure that can help to protect structures and equipment from the damaging effects of lightning strikes. By installing a lightning protection system, you can significantly reduce the risk of fire, explosion, electrical damage, and injuries. Here are some additional details about lightning protection systems. Lightning protection systems should be designed and installed by qualified professionals. Lightning protection systems should be inspected regularly to ensure that they are functioning properly. Lightning protection systems should be grounded in accordance with the National Electrical Code, or NEC. Lightning protection systems should be bonded to all metal objects on the roof of a building, such as antennas and satellite dishes. Here are some tips for protecting yourself from lightning strikes. Seek shelter indoors during a thunderstorm. Avoid contact with metal objects, such as fences and power lines. Stay away from windows and doors. Do not use electronic devices, such as cell phones and computers. If you are caught outdoors during a thunderstorm, crouch down low to the ground in a ball-like posture. Avoid standing under trees or other tall objects. Stay away from water. Now, we will explore more information about grounding rods. Grounding rods are metal rods that are driven into the ground to provide a low resistance path for electrical current to flow to earth. They are an essential part of electrical grounding systems, which are used to protect people and equipment from electrical shock and damage. Grounding rods are typically made of copper or galvanized steel and are available in a variety of lengths and diameters. The size and type of grounding rod required for a particular application depends on the size of the electrical system and the soil conditions. The National Electrical Code, or NEC, provides detailed requirements for grounding rods, including the minimum size and type of grounding rod that must be used, as well as the methods for installing and connecting grounding rods. Grounding rods must be installed in accordance with the NEC requirements. Grounding rods are typically installed by driving them into the ground using a hammer or a power tool. The top of the grounding rod should be buried at least 8 feet below the surface of the earth. The grounding rod must be connected to the electrical system using a grounding conductor, which is a wire or cable that is sized according to the size of the electrical system. Grounding rods should be inspected regularly to ensure that they are in good condition and that the connections are tight. If a grounding rod is damaged or corroded, it should be replaced immediately. Grounding rods are an essential part of electrical safety. By providing a low-resistance path for electrical current to flow to Earth, they help to protect people and equipment from electrical shock and damage. Here are some additional details about grounding rods. Grounding rods should be installed as close as possible to the electrical equipment they are protecting. Grounding rods should be driven into the ground at an angle to increase their surface area. Grounding rods should be connected to the electrical system using a grounding conductor that is made of copper or aluminum. Grounding rods should be inspected regularly to ensure that they are in good condition. Here are some tips for installing grounding rods. Choose the correct size and type of grounding rod for your application. Drive the grounding rod into the ground at an angle. Bury the top of the grounding rod at least 8 feet below the surface of the earth. Connect the grounding rod to the electrical system using a grounding conductor that is made of copper or aluminum. Inspect the grounding rod regularly to ensure that it is in good condition. And now, we will explore grounding blocks. Grounding blocks are used to provide a convenient and reliable point for connecting multiple grounding conductors together. They are commonly used in electrical systems to connect the grounding conductors from different pieces of equipment or from different parts of a building. Grounding blocks are typically made of metal and have multiple terminals or connection points for attaching grounding conductors. The terminals are usually designed to accept a variety of wire sizes and types. Grounding blocks are available in a variety of sizes and shapes to accommodate different applications. Some grounding blocks are designed to be mounted on a surface, while others are designed to be flush-mounted. Grounding blocks should be installed in accordance with the National Electrical Code, or NEC. The NEC provides detailed requirements for grounding blocks, including the minimum size and type of grounding block that must be used, as well as the methods for installing and connecting grounding blocks. Grounding blocks should be installed in a location that is accessible for inspection and maintenance. The grounding conductors should be connected to the grounding block using approved connectors. Grounding blocks should be inspected regularly to ensure that they are in good condition and that the connections are tight. If a grounding block is damaged or corroded, it should be replaced immediately. Grounding blocks are an essential part of electrical safety. By providing a convenient and reliable point for connecting multiple grounding conductors together, they help to ensure that all electrical equipment is properly grounded. Here are some additional details about grounding blocks. Grounding blocks should be made of a material that is compatible with the grounding conductors. Grounding blocks should be sized appropriately for the number of grounding conductors that will be connected to them. Grounding blocks should be installed in a location that is protected from moisture and corrosion. Grounding blocks should be labeled to indicate the purpose of the grounding conductors that are connected to them. Here are some tips for installing grounding blocks. Choose the correct size and type of grounding block for your application. Install the grounding block in a location that is accessible for inspection and maintenance. Connect the grounding conductors to the grounding block using approved connectors. Ensure that all connections are tight and secure. Label the grounding block to indicate the purpose of the grounding conductors that are connected to it.